Hello everybody, my name is Tevfik. Today I'm going to speak about kick tolerance in our proof of concepts video designs video series. So this topic is basically a follow-up topic from the last video where we have derived the equation for estimating the hydrostatic pressure in the gas column, and that was basically using the compressibility factor concept of real gases. So let's start with the definition of the kick tolerance. So the kick tolerance is, if you go look at the 1991 Messelentar definition, it's basically a safe amount of volume that we could shut in and circulate using the Driller's method without exceeding our fracture pressure at a known kick intensity. So, like the kick tolerance, there are several definitions existing in the literature, in the drilling industry, drilling engineering expertise area. So the kick intensity is for this purpose of this video and for most commonplace that I've seen, is basically equivalent mud weight above the mud weight. Let's say mud weight in use. Let's say if I have a 0.2 SG kick intensity, which means that I have a kick information which is 0.2 SG in excess of the mud weight in use. So in order to drive our equation for the maximum allowable height, we need to draw a simple schematic basically. So I have the pore pressure at the TD, and that is at a known kick intensity, and then I have an influx height which is x, or maximum allowable height, that's in TVD. All the depths are in TVD. All the lengths are in TVD. And then I have the mud column of y. All right, original mud weight column of y, and then the original mud weight column above the shoe. So basically I have the fracture pressure at the shoe. That's the basically I will set my limit of the resulting pressure to the fracture pressure, so that I could basically shut in and circulate the kick out using the Driller's method. So there's no basically kill mud involved in the first circulation. So going back again to our equation of basically equating all the columns to the fracture pressure. I have fracture pressure on the left hand side, and on the right hand side I have the pore pressure, and using the principle of summation or subtraction of the hydrostatic, and then I go with the TVDs. So I have the pore pressure minus the gas column, the hydrostatic associated with the gas column, minus the hydrostatic pressure associated with the mud weight in use, or original mud weight, let's call it. So if I expand the equations, I basically take out the 0052s just to have a simpler formula. And then here what we need to define is this pore pressure. We are going to define it as mud weight plus the kick intensity, so that we can get rid of some components, and it makes more sense that we can talk about both the kick intensity and some other concepts. So on the left hand side we have the fracture pressure at the shoe. On the right hand side we have the pore pressure, which was rewritten as mud weight plus the kick intensity. And then this is the depth of shoe plus the x plus y. All the TVDs is equating to the TD of the well. All right, and then plus and then also the associated column of hydrostatic column of gas influx, and the associated column of the y. So I basically write that over here, and then this one is over here. So I expand this term over here, as you can see. So that becomes the mud weight times the depth of shoe, and then plus the mud weight plus the times the x plus y, which is below the shoe, the TVD below the shoe to the TD. And if you continue to expand, you could see that this formula becomes the kick intensity times TD, and then your mud weight times the y is gonna cancel each other, because when we were talking about the initial the subtraction from the TD, we said pore pressure minus the gas column minus the mud column is gonna be equal to fracture pressure. That's why we set the limit, and you have the subtraction of a mud column times y, and then you have the plus mud weight times the y, so they will cancel each other, and then you are going to end up with fracture gradient that times the shoe, and then mud weight times the TD of the shoe, plus the mud weight times x, that's the influx height, and plus the kick intensity times the TD, and then minus the influx density times x, which is the associated height. So I basically take this term to the left, so that I can basically put a common bracket and then put the depth of shoe on to the left hand side, and on the right hand side I have the difference between the mud weight and the influx times the associated height, and plus the kick intensity times the TD. So then what's going to happen is I basically will solve for x being the TVD of the maximum allowable height that basically we could shut in and then circulate, and if I solve for x, it will be depth TVD of the shoe, and then multiply by the difference between fracture gradient and the mud weight, minus the kick intensity times the TD, and then minus, I put an M star in blue, and then on the denominator I have the mud weight, the difference between mud weight and the influx weight, so both in the same dimension or same unit. So let's talk about the M star over here. So M star over here is a margin, okay? So I put the margin over here as well, because if I want to account for a dynamic kick tolerance, then I need to account for in a circulating condition. If I have let's say a long choke line, I need to account for the choke line friction. Also, I might need to account for basically the annulus friction inside the shoe. Although most of the cases it's negligible, especially in the kill rates, in the smaller rate, but it's a consideration again. It could be also during the circulation an error, or basically the choke operator might close the choke more than is required. That will basically put more pressure into the valve. So that will put pressure everywhere in the valve, including the shoe. That's why it needs to be subtracted over here, or in this case it's a plus over here as an additional pressure. So if we basically solve for x, what is going to happen is it will go into the minus side over here, okay? Or it could be also an overbalance that you want to place while circulating the kick. For example, I have established my shut-in pressures, and then I would like to achieve 100 or 200 psi overbalance, and then you will basically pump into the well, and then that will put pressure everywhere. Also, so that can be also considered in under M star. It could also, what else it could be? It could also be a additional back pressure if MPD is being used. So that there will be choke where the flow is going through, and then if there is a back pressure over there, then that will cause the x, the height of the influx, maximum level height, to go down, while by incorporating this minus M star as margin to account for all these effects. So I wrote this part intentionally in a longer term. You could write in a shorter version. You could simply call this as a MASP, which is maximum over annular surface pressure. That's written over there. So it's basically the difference between the margin between your fracture gradient and the mud weight is quite important during killing the well. But it could be also written as a MASP. Or you could take this term and the M star term. You could say it as a MASP, revised MASP, or something like that. Okay. So we talk about the kick intensity. So kick intensity, it could be 0 over here. let's say if your mud weight is basically is dictated by a wellbore stability, and your pore pressure is much less than that one, you will not account for a minus. You will account for a zero kick tolerance, so that will not have any associated effect on the X. So let's look at these parameters. Which parameter define how the parameter change in one term, how it's gonna affect the other parameter. So we look at the kick intensity. So if I have let's say a higher kick intensity, so we assume 0.2 SG. Let's say if we assume a 0.5 SG kick intensity, meaning that we have a higher pore pressure that is basically giving the influx, which means given that I have a same strength of shoe, I can now tolerate a less height of influx without breaking the shoe or exceeding the fracture pressure. So if of course if the fracture gradient is higher at the shoe, which is a stronger shoe, then you could obviously tolerate a higher X over here, higher X over here on that column. And then if let's say my mud weight approaches the fracture gradient, then our mass value is reducing, and also our height that we could tolerate is much less, because when you are circulating, the kick casing pressure will follow kind of a term like this, profile like this. So this increase will not basically tolerate any more mud weight approaching the fracture gradient. So I put if the mud weight in use is approaching the fracture gradient, X, which is the height, will also approach to zero, and mass also will approach to zero, if you could think about the limit. Yeah. And then the next one is the M, the margin. Of course, if you want to account for everything, the choke operator error, any overbalance, any choke line friction, or any back pressure, then what's gonna happen is, of course, that all those accounting will be an addition or into this shoe pressure. Then that's gonna obviously drive the associated height of the X, maximum level in TVD, go to drive lower, so that you can tolerate a less height. And finally, the influx density. So if I have a lighter fluid, and then what's gonna happen is that reduces, and then this mud weight plus the influx is gonna drive up, and then X will gonna drive down. So how we think about it in another way. So if I have let's say a lighter influx, all right, if I have a lighter influx, if you think about total hydrostatic reduction over here, or total hydrostatic over here, okay, if I have a lighter influx, if I take the difference between the pore pressure and the light influx plus the hydrostatic, I'm gonna have a higher shoe I'm gonna have a higher pressure at the shoe. However, if you think about same height of influx with a higher density, what's gonna happen is you will have a higher hydrostatic over here, because you have a higher gas gravity or gas density. Then you will have a higher hydrostatic column, which will result pore pressure minus a higher hydrostatic column is going to result into less pressure at the shoe. So you can basically, with a heavier one, you can tolerate a longer height of X instead of with a lower influx, very light fluid. You can only tolerate a less height of TVD without exceeding the shoe pressure. So then I think we are good on this page. Let's go to the second page. So okay, so kick tolerance, what's the application? So when the different oil and gas companies and IOCs that I work for have different kick tolerance requirements for different hole sections. So they tend to basically reduce with the hole sections hole diameter reducing, because same amount of volume, if you put it on a smaller hole diameter, it will occupy a higher height, which will basically which will drive the kick tolerance into a different state. Therefore your let's say if I have a 50 barrel for 12 and a quarter section, then I have a 30 barrel, because the associated height is much higher if you take the same volume, and then if you put it on a smaller hole diameter. So as we said on the first page, the kick intensity, if I have a case that basically almost depleted formation, or let's say take a depleted formation, and then the mud weight is driven by the wellbore stability, then you are most likely your kick intensity in that case is probably more practical to take it as zero, because your mud weight is already driven by the wellbore stability, which is much larger than the pore pressure, instead of accounting for another kick intensity on top of a mud weight, which is already overbalancing your pore pressure. Basically it tells you that that pore pressure isn't real, isn't there. Okay, so let's move this. Let's look at this formula again. Our formula again. So the formula was basically a simple height, associated height, maximum allowable height, being the multiplication of the depth of shoe times the fracture gradient minus the mud weight in use, minus the kick intensity times the TD, minus any margin. We put this in blue, so let's mark it in blue again. Okay, and then the denominator, we have the difference between the mud weight in use and the influx. So, and we defined the kick intensity being the kicking pore pressure minus the mud weight in use. And remember, everything, this height x is in TVD over here. So how you convert, or how you use this concept? Basically, we talked about the kick tolerance requirement for each hole section. So you have a requirement of a volume. Basically, if you have kind of a fracture gradient in the hand, then you could get an associated height, and then from that associated height you can come up with a volume, and then you will then compare. Okay, that volume, is it in the guideline? Is it satisfying the guidelines, or do I need to do something different? Either if your fracture gradient is less than you expect, or if you do let's say FIT for a development vest, you could try to strengthen the shoe, but the circle or the loop becomes starts with X, and then of course, depending on the kick intensity is also a company defined concept. Some companies might say, okay, use the kick intensity in terms of the mud weight, density of the mud weight over the mud weight, percentage of the mud weight, or they could just simply give 0.2 Hg, as we discussed on the first page. And then as I mentioned, this one we could go between the fracture gradient, kick intensity, and the X, and I will talk about the influx density as well. So how we convert from X to the volume. So first of all, we have an X associated height, and then we have the capacity around the drill pipe. Okay, so let's take a case that the influx of the height is located at the shoe. All right, so then I can basically calculate the capacity. So you have the capacity of open hole slash the drill pipe, or let's say heavy drill pipe. You can get a volume, and then I will call it as V shoe. All right, so we call it as V shoe over here. Okay, And then here, just to mention that again, if I look for the x in TVD, you are talking about the capacity times x over there. However, x you need to go to the MD. I think in some spreadsheets they try to convert it in the cells, but I think the best way, in my opinion, is take the survey listing or planned survey listing, and then basically take the x from there in TVD and then convert the measure depth. That measure depth goes to the capacity equation to get a volume from there. I think that's the cleanest solution. And then you look at two scenarios then. So you have the volume, and then you need to send the volume to the bottom of the well. So you can allow for some kind of an expansion, and then in order to take that volume to the bottom, you can simply use the Boyle equation, which is P1 V1 equal to P2 V2, or you could basically use the compressibility factor that we have covered using Abu Kasum and Dranchik equation, because you have the pressure, you have the temperature, and you have the specific gravity of the gas. I think in a producing field it's a bit simpler to get the composition of the fluid and then get the specific gravity. So with the temperature, pressure, and the specific gravity, you can find the compressibility factor at the shoe and at the bottom. So the shoe is being the basically the fracture pressure, because that was our limit, you remember, and then at the bottom I have the pore pressure at a known kick intensity, so that I could basically solve for the V1 over here. As we mentioned, you could simply use the Boyle's law. However, to make it more accurate, we could easily calculate the Z if we have the specific gravity, pressure, and the temperature. And then the other one to look at it is basically simple moving this height of the influx in TVD to the bottom of the well. Again, this is in TVD. So TVD, I would if I take the survey listing and then convert to MD, because I'm assuming I have a different inclination and then azimuth profile from the shoe to the TD. Then you could come up with an X, and then basically a multiplication with the capacity. Of course, that capacity, that height over here, this height will be the measure depth of the conversion from X, and then the capacity between the open hole and the BHA, that's going to give you a V2, and then your kick tolerance will be basically the smaller of the V1 and V2. So the idea behind this iteration is basically you allowing your kick to expand while going up the hole, and then in some cases, for example, where your depth in one of the development well that we have done, so the distance between the shoe and the let's say you have a very short open hole section, and then you see that if you multiply the fracture pressure times your initial volume, and then if you convert to the bottom hole volume, you get a much more volume at the TD. That's fundamentally that will give you a fundamental mistake, where basically it is going to expand higher to surface. So that's the point where you take. That's the idea, where you take a smaller of these two, so that you allow the expansion of the gas. All right, and then as we mentioned, if you use I think compressibility factor, that's going to be a more accurate calculation. So the other one of the other approach that I came across in one of the paper is basically if my kick height is less than my BHA, then what we could say, they were recommending basically the kick at the top of the BHA, and then basically converting to the bottom volume using the same equation, because still account for the compressibility factor, and then it results basically a smaller volume, so that will give you a more conservative volume, and then again you will it was recommending to compare this V3 and the V1 to basically and then the final kick tolerance will be the smaller of these two. But if you look at this case, then obviously the kick tolerance will be more conservative than this volume. And then also, if the BHA is, let's say, short, and then if the pressure regime is very similar, if there is no let's say a rapid increase in pressure, you would expect a similar volume over here, because yeah, I mean the multiplication of the temperature, pressure, and the temperature, pressure, and then the compressibility factor will not be too much different across this BHA. So it's another approach. Okay, and then so the kick tolerance application over here. So I think in the wells that basically in the wells that basically, so you do your FIT or leak off test at the shoe, and then you have basically with the shoe strength, and then with the TVD associated height converted to volume. If it's below your company minimum company specified kick tolerance requirement, then we talk about some contingencies on at the shoe that can be done at the shoe, or you are talking about shortening the TD so that you have basically a lower pore pressure to kick, and then also that will imply some contingency casings, additional casing strings. But again, additional casing strings, and on the other side, let's say if you have a sufficient shoe that you could basically carry the casing deeper, but then yeah, you will always come to this limit of the design limit. So if you remember the triaxial design limit that we have derived, and then we plotted in an Excel spreadsheet, so it's the new or the revised TD needs to be checked against those worst case loads to make sure that it's still in the performance in the performance limit, satisfying our basically company guideline design factors. That's another thing. So just before closing it, I would like to look at this bottom-up design, conventional bottom-up design. So this is another basically application of using a kick margin on this plot, because so you have the, let's say, fracture gradient, and then you have the fracture gradient minus the kick margin. So if let's say I do not have a margin from the mud weight to the fracture gradient, over here in this equation, it's gonna drive my mass down, it's gonna drive my x down, which was the associated height, that basically that's allowable height of gas, so that I have the basically I don't exceed my fracture pressure. So if you basically tighten this area, tighten this distance, it's gonna drive that down. So that's another reason why you basically put a kick margin, into kick margin. How do you say, reduced gradient or revised FG curve to allow to allow some volume for the kick tolerance, so that you can basically shut in safely, and then also circulate safely using the Dirichlet method at a known kick intensity. Alright, I think we have covered most of the things. So I talked about, yeah, it's similar to Boyle law, but you have the data in the hand, so why not spending a little bit more time to find the compressibility factor and then to make the equation better. I think, yeah, there's I've seen at least two spreadsheets to calculate the kick tolerance in different companies. Sometimes the formulas may get corrupt, or someone makes a change in the formula and then basically shares the spreadsheet. It's always good to understand, or to basically understand the concept behind the kick tolerance, or another concept that like we have done in casing design. So you could simply take your calculator and then to see if you can make sense of the numbers or not. Other than rather than it's a very as we have shown, it's a very similar it's a very simple formula to come up with, not like the deriving for the delta P for the traction design, but it's always good to understand the concept, and then if it's a simple enough calculation to put in the calculator, then yeah, it's good to understand that one. Okay, thank you very much.